Chapter 8. Here's a little review of projectile motion. Consider a projectile with launch speed v sub 0 and launch angle theta above the horizon. In Chapter 4, we found that the distance that this projectile travels before it returns to the same elevation from which it was launched, called the range, is v sub 0 squared times sine of 2 theta divided by g. And here are some plots of the parabolic trajectories of a projectile launched all with the same speed of 99 meters per second, but at different launch angles, 15 degrees, 30 degrees. The maximum range is achieved at 45 degrees, where sine 2 theta is maximum. All of these results neglect the effects of air resistance, but in real life, the effects of air resistance or drag are too large to ignore. If you do include drag, the angle for maximum range depends on both the size and the mass of an object, and it's typically about 35 degrees if you look at baseballs. If you look at golf balls, it's even less than that, so about 15 degrees. The acceleration of a typical projectile subject to drag force from the air is in components. The x component of the acceleration is due mostly to drag, negative rho ca over 2m times the x component of the velocity times the speed, and the y component of the acceleration is minus g, as it would be for any projectile without air resistance, minus, again, this drag component. Negative rho ca over 2m times the y component of the velocity times the speed. Both of these components are not independent of each other, so a sub x depends on both the x component of the velocity and the y component, and a sub y depends on not just the y component of the velocity but also the x component. So you cannot solve these equations with just writing down another equation. You have to use a computer to numerically simulate this solution. And that's what is shown here, is a computer simulation of a 5-gram plastic ball shot with different angles. And it turned out here that the computer showed the maximum range angle was 30 degrees. Okay, uniform circular motion. When you're describing uniform circular motion, it's convenient to set up a new coordinate system that it's actually moving and rotating. And it's the r, t, and z coordinates, where the r-axis always points towards the center of the circle. So here it points this direction. Up here it points up and to the left. The t-axis always points tangent to the circle at right angles to r, but it's still in the plane of motion. And the z-axis points perpendicular to the plane. This way, if you've got a particle in uniform circular motion, its velocity is always in the t direction along the t-axis, and the acceleration is always along the r-axis. So if you look at the r, t, z components of velocity and acceleration, they look like this. V sub r is always 0, v sub t is always omega times r, and v sub z is always 0. A sub r is always the centripetal acceleration v squared over r, which if you use omega, it turns out to be omega squared times r, where omega is v over r, the angular speed. A sub t is 0 for uniform circular motion, and a sub z is 0. So an object in uniform circular motion is not traveling at a constant velocity in a straight line. Consequently, this object must have a net force on it. The net force is the mass times the acceleration, and in the case of uniform circular motion, it's mv squared over r towards the center of the circle. If there was no force, the object would continue on a straight line, and if the road is a circle, the car would end up in the ditch. Here's a picture of a car on an actual racetrack which is banked to allow the normal force to provide some of this net force needed to provide centripetal acceleration. This figure shows a particle in uniform circular motion. There's a net force in the r direction, pointing towards the center of the circle. This centripetal force is not a new force, it must be provided by familiar forces we already have from previous chapters. And here are the components. The net force in the r direction is m times a, which is mv squared over r. Or in terms of omega, it's m omega squared times r. The net force in the t direction is 0, so it's not speeding up or slowing down. And the net force in the z direction is 0, it's not going up or down. So real highway curves are banked. So if you look at the top view of a car going around a curve, you see this circular curve, there's the velocity, there's the radius of this circular path, center of the circular path. If you look at the rear view of the car is driving away from you down into the page here. Here's the center of that circle going off to the left horizontally, and here is the banking angle, theta, of the curve. So if you draw a free body diagram of the car, you have gravity acting down towards the center of the Earth, and the normal force acting up at an angle theta to the z-axis. So this normal force has a radial component which must provide the centripetal acceleration needed to turn the car. And it turns out, you can work this out, and it's worked out in the textbook, that for a curve of radius r banked at an angle theta, there is an exact speed at which a car must take the curve to have zero friction, and that's the square root of r times g times tan theta. If a car is going faster than that speed, so here's a free body diagram of the same car with speed greater than square root of rg tan theta, then static friction between the road and the wheels of the car must point down the hill to prevent the car from slipping up the hill. So summing up, a faster speed requires a larger net force towards the center of the circle, in order to provide enough centripetal acceleration. The radial component of the static friction adds to the radial component of the normal force to make the car turn. And maximum speed occurs when the static friction reaches its maximum, mu sub s times the normal force. If the car is going slower than this square root rg tan theta, then static friction must prevent the car from slipping down the hill, so it acts up the hill. Summing up, without a static friction force up the slope, a slower moving car would slide down the incline, as it would if, for example, if it was stopped, it would just slide down the hill. So another way of saying that is that the radial component of the normal force is too much for circular motion if the speed is less than v sub 0. So the radial component of static friction reduces the net radial force. Okay, let's talk about circular orbits. We'll start by looking at this little portion of a smooth, spherical, airless planet with one tower on it of height h. The projectile is launched horizontally, parallel to the ground, with an initial speed of v sub 0, and if v sub 0 is small, as in trajectory A here, it simply falls to the ground along a parabolic trajectory. And this is what's called the flat Earth approximation. If you're near the tower and the projectiles are going slowly, then we can approximate the spherical planet to be about sort of flat near the tower. As you increase the initial speed, the range increases, and since the Earth is not flat, the ground curves away. So if you look at trajectory B, as it goes along, it falls further and further down until it lands way over here, which is well along the curve of the planet. Trajectory C is even further, goes right around halfway around the planet before it finally hits. Okay? And if v sub 0 is sufficiently large, there comes a point where the trajectory and the curve of the Earth are parallel. This is trajectory d. As the projectile falls, it never gets any closer to the ground, so that by the time it's gone right around, it's still at the height h away from the surface. This is called, trajectory d is called an orbit. So figure A shows this flat Earth approximation, which up until now we've been using. The force of gravity on an object of mass m is m times g vertically downward, and as the object moves, that direction of that force does not change, so we have a parabolic trajectory. In reality, with very, very fast moving objects on spherical planets, the real force of gravity is towards the center of the planet. Okay, this is not a constant direction force, but it's more like a centripetal force that's constantly towards the center. So it's F net divided by m is g towards the center. If this is a circular orbit, then this acceleration must be the radial component of the acceleration, centripetal acceleration, which is v squared over r, where v is the speed of this orbit. Okay? And that must equal g if it's gravity. So we can solve this equation for the orbital speed, and it turns out to be the square root of r times g. This is the required speed for a circular orbit near a planet's surface, neglecting air resistance. So if you have, like the space shuttle in a low Earth orbit, you can find the period of how long it takes to go around the Earth by 2 pi r is the circumference divided by the speed, and you end up with 2 pi times the square root of r over g. So you can make a calculation if you use the radius of the Earth, which is 6,400 kilometers, and you know g is 9.8, you can figure out that it takes about 90 minutes for a satellite in a low Earth orbit to orbit the Earth, which is true. Okay. If you're in this spacecraft, you're constantly in free fall, falling under the influence of only the gravity force. This is why astronauts on the Space Shuttle or the International Space Station feel weightless. Okay, I want to talk about fictitious forces. So if you're in a car and the car makes a sudden stop because someone pushes on the brakes, you seem to be hurled forward. So in the passenger's perspective, the car is at rest, and there is this force you feel somehow which is throwing you into the windshield. Okay? This is called a fictitious force that you experience because you're in a non-inertial frame. Okay? We're not really going to calculate fictitious forces, but we'll just mention that you can work in a non-inertial frame by describing fictitious forces. But they're not real because there's no agent exerting them. Okay? They're just used to describe your motion relative to a non-inertial frame. What we will do in this textbook is we will always do our calculations in an inertial reference frame, such as that of the ground. In that case, what's happening is the car is decelerating. You have a normal force on you going up and a gravity force pulling down. Those are the only real forces on you. And what will happen is you will continue forward with a constant velocity as the car decelerates, and that will cause your position relative to the car to go forwards. And you'll still hit the windshield in either case. So here's a bird's eye view of you riding in a car as it makes a left turn. So from an inertial reference frame, what we will do in this course is we will note that there's a normal force on of the door of the car on you pushing you inward that keeps you in the car. Even though what you want to do is you want to keep trying to move straight ahead. That's your inertia, which wants to pull you off into the ditch. Now, if you were to look at the fictitious forces and imagine life relative to the non-inertial reference frame of the car, I guess you would feel pushed towards the outside. This fictitious force is referred to as the centrifugal force. And there really is no such force if you look at the inertial frame of the ground. Let's think about gravity on a rotating Earth. So here is a picture of the Earth and sort of an enlarged, not to scale diagram of a spring scale weighing an object of mass m on the Earth's equator. So here you're observing from some position above the Earth's north pole. You can see this spring scale on the equator, and the force of gravity of the Earth on the little mass m points directly towards the center of the Earth. So if you rotate this and look at the little free body diagram, you have two forces on the mass. One is the force of gravity pulling down, and one is the spring scale force pushing upwards on the object. So if we were to assume that the spring scale was measuring the actual force of gravity, then the fact that the Earth was rotating would weaken our measurement, or would reduce our measurement of the gravity force. So the free fall acceleration we would measure in our rotating reference frame is force of gravity that we measure divided by m, which would be F, the actual force of gravity, minus m omega squared times r. So solving that out, we get the actual acceleration due to gravity minus omega squared times r, where r is the radius of the Earth. Let's think about roller coasters. So here you have a vertical circular track and a cart with a person in it that's going around at some speed. Okay, this is not actually uniform circular motion, because at the bottom of this circular motion you're going some high speed, and as you climb up and up and up, there's a slowing due to gravity, and so you'll go slower at the top. But at the very bottom and at the very top points, the track is momentarily horizontal, so the acceleration it's not slowing down or speeding up, the acceleration is purely centripetal. And because at all times the car is moving in a circle, there must always be a net force towards the center of the circle. So here's a free body diagram of the car when it's at the bottom of the circular motion. Okay? You've got the normal force pushing up and got gravity pulling down. Since it's on a circular path and the center of the circle is above, the net force must point upward at this point, meaning that the magnitude of the normal force must be greater than the magnitude of the gravitational force. This is why you feel heavy at the bottom of the valley of a roller coaster. It's because you're feeling this increased normal force. If you want to work out the net force in the r direction, it's the normal force, radial component, which is n, plus the radial component of the gravity force, which is negative mg, and this must equal the centripetal force, mv squared over r. If you solve this for the normal force n, you get the normal force is mg plus mv squared over r. The normal force is larger than mg. Here's the roller coaster at the top of the loop. In this case, the center of the circle is down. Okay. The normal force must press down on the wheels, as the car is upside down. And the car is still moving in a circle, so the net force, which is the radial component of n, which is n in this case, plus the radial component of the force of gravity, which is positive mg in this case, must equal mv squared over r. Solving for n, we find that the normal force is mv squared over r minus mg. And so if v top is large enough, this can actually be bigger than mg. Okay, so here again is that equation for the top of the loop. Notice that if the speed, v top, decreases, there comes a point where the normal force will go to 0. You can solve for this critical speed, v sub c, is when n equals 0, you get the square root of r times m times g divided by m, which is just the masses cancel, you get the square root of r times g. This is the slowest speed at which the car can complete the circle without falling off the track near the top of the loop. So going through it again, if the car is going very fast, the normal force adds to the gravity in the downward direction to make a large enough force for the car to turn the circle. At this critical speed, v sub c, gravity alone is enough to force the car to turn on the circle, and you don't need any normal force, so it goes to 0. If you were to decrease the speed even more, what would happen is that the gravitational force would be too large for the car to stay on this circle, so it would curve even more, and in fact just fly off in a parabolic trajectory. And way back here is where the normal force would go to 0, and here you're just flying through space, which doesn't look too safe. Okay, so to finish off Chapter 8, I want to say a few words about non-uniform circular motion. So here's an object moving a circle. We have this reference line used for measuring angles theta as it moves. This object has a velocity which is always tangent to the circle. So the radial and the radial component v sub r is always 0. That's how it stays on a circle. You can use the angular velocity omega to describe the rate of change of theta. It would be positive for counterclockwise rotation, negative for clockwise rotation. And if the object has tangential acceleration, a sub t, then it will be changing its speed. It always has a radial component of its acceleration, a sub r, okay, which causes it to stay in the circular path. So this figure is this particle is speeding up as it moves in the circle. So the tangential acceleration is d by dt of v sub t. This can be described by the angular acceleration alpha. It's equal to r times alpha. So, and if you want to look at a sub r, the centripetal acceleration, it's v squared over r, which is omega squared times r. So in terms of the angular quantities, you can use the equations of constant acceleration to find the theta final in terms of omega initial and alpha. You can find omega final as omega initial plus alpha delta t, and you can use this equation to find omega alpha if you know the initial speed and the angular acceleration and the angular distance it traveled. So keep in mind a net force is being applied to this object, and F net could be due to various forces, tension, thrust, friction, but it can be decomposed into two components: the tangential component, which causes the particle to change its speed, and the radial component, which keeps it on this circular path. So if something's speeding up and going around it in a circle, the net force will be on this diagonal, part of which is towards the center and part of which is causing it to speed up in the tangential direction. And keep in mind, we can use Newton's second law in the RTZ coordinate system that's going along with the particle. The net force in the radial direction is always mv squared over r, or m omega squared r, depending if you're using v or omega. The net force in the tangential direction is m times whatever the tangential acceleration is. And there's no net force in the z direction because the particle is staying in the plane of rotation.